Hello everyone, welcome to the control system. This is part 7 of lecture 6 on state space representations, and in this section we'll discuss the state space representation of scalar differential equation system. And there will be a lot of mathematics, but I think it is not so difficult for you. So far we have discussed the general state space model, know how to form the state space model, and plus we already know how to do the numerical integrations in MATLAB. In this section, we'll discuss a little bit of mathematics behind them. So the state space, first let's consider the state space representation of an order, this is R right here, system of linear differential equation in which the forcing function does not involve the derivative terms. So basically it have only u, there is no u dot or u dot dot. So in this case, we know the initial condition of the state and together with the input, all right? So like from the previous lecture, previous part, you already know that with the knowledge of the initial condition and the input, you can determine the future behavior of the system. Okay. So in this case, let's represent the state by these equations. So vector x consists of x1 until xn, and x1 is y, x2 is the derivative of x1, and so on until y derivative of n minus 1 of y dt n minus 1. And then by rearrange the term, not rearrange, by replace the term. So y here is x2, you just replace this by x2, and then x3, and so on. So the final part is xn, okay, xn right here. Okay, and the state space equation become like this. So from this equation to this equation, it's the same, but this one is in matrix form, and this is matrix A, this is matrix B, this is matrix C, and there is no matrix D. Okay, we assume that D equals to 0. And you can also find the corresponding transfer function, which is given by this. Another one is a state space representation of an ordered system of linear differential equation in which the forcing function involved the derivative terms. So consider this differential equation. You can see there is input u and the derivative of u, so until u end. Okay. So the important part is to choose the state and how to represent the state. So there are many ways to represent the state, but in this case, we just choose x1 equal y1 y minus beta 0 u, and beta 0 is a constant number equal u b0. Okay, so b0 can be found in the equations, this one. And x2 equal y dot minus beta 0 u dot minus beta 1 u. So, but you need to know that beta 0 and beta 1 can be found in this. It can be determined like this, and so on. It's a little bit of mathematical, but you can refer to the textbook if you miss some part. So in terms of a vector matrix equation, the state equation and the output equation can be written like this. Okay, by just rearrange the term. So this is big matrix A, and this is matrix B. This is matrix C. Okay. And you can also find the corresponding transfer functions as well. Thank you.